Hi everyone, I'm Zengqun Zhao, and I'm currently a third-year PhD student at Primary University of London. And sorry. So this morning, there's so many very nice work on how to use the very language models to do video understanding. But our work is more like how can we use the pre-trained large very language model to improve the video generation performance. I don't know how many people are working on this area. Just a very quick look of the diffusion precise. So it's a very high-level idea of diffusion model is to learn to generate data by reversing gradually noising precise. So it contains two parts of the precise. The first one is the forward diffusion, which corrupts a data point, for example, an image, by gradually adding Gaussian noise and ultimately resulting in the pure Gaussian. And during the generative process, the model will learn to approximate the reverse to gradually remove the series of noises and recover for example, the image with salient features. So the video diffusion model is built on this diffusion precise, but the only difference between the image is it will learn a 3D layers or 3D cross modality in the transformer. And currently, there are two groups of foundation models for video diffusion model. The first one is quite the earlier research, which is based on UNet. And currently, most of the state-of-the-art models are based on the diffusion transformer. For example, some VO3 or some open source models like Hunyuan Video or Coq Video X or One. So the motivation of doing inference time scaling for video diffusion model is there are quite some limitations for the current video diffusion model. The first one is once the model is pre-trained, then the capacity is fixed at inference time. So it's very hard to scale for some complex prompt. And also in diffusion model, the quality depends heavily on the random initial noise, which means the unstable results will caused by the randomness. And also, even like some like state-of-the-art models like VO3 or other open source model, the temporal inconsistency and the motion artifacts remain unsolved. And also, if we want to do some fine-tuning or retraining for the video diffusion model, it's very hard. Normally, we can't do it in the university because it needs like 64 GPUs for the fine-tuning. So if we do the inference time scaling, so then we can improve the video quality without retraining the model. And also, it allows the test optimization. For example, we can optimize the noise, the trajectory of the diffusion, and also we can do the refinement for the latent. So instead of like scaling the model, we scale the inference process. There are quite some research try to investigate to this. For example, they try to optimize the initial noise. For example, these papers, they try to use the denoise latent and use in the Fourier transformation to get the lower frequency and then merged with another new Gaussian noise, which is extract the high frequency and then re-initialize the initial noise. And also some people, they try to do some warping on the initial noise. For example, how I warped your noise in this paper, they initialize all of the noise exactly the same, and then do some small change, small warping in the initial noise. Or they can use some reference video and then extract the optical flow and then warp the initial noise. Then the generated video will follow the motion pattern. Another research line is searching. So they try to search. They have several candidates. Then they can search which one can be the best candidate for the generation. Then we can improve the quality. So currently they use like evolutionary search or beam search. Some people also use the very slow like a best of them. And for both the optimization or the searching methods, they have a limitation, which is inability to evaluate the intermediate latents. So this will result in the errors introduced at the initial stage and then accumulate across the whole trajectory. So our paper, we try to evaluate the latent in the very early stage of diffusion process. Then we can do some earlier decision, and we can accept and reject some late candidate. So this again, this is diffusion, just the regular diffusion process. We have a pure noise zeta t, which is a latent noise, and then we have several denoise steps to get the final clean latent Z0, and then we use the VAE decoder to get the final video. Instead of like doing this pipeline, first we do we generate some candidates based on this zeta t, which is some variations based on this pure Gaussian noise, and then we do generate diffusion process for each of them. So this only happens in the very earliest stage, so it won't take too much computation. And in a selected step, we use we proposed a latent real model, which is based on the real language model. This model will evaluate all of the samples, so this resampling is we propose to sample the candidates according to the reward normalized probabilities. And then we only keep the selected samples and drop the undesired one. And then we will continue with the generation for the rest of the candidates. And again, we do the selection on the selected steps. And again, do the generation, continue the generation. And in the final searching scheduler, we do the pruning, which means we select a only one candidate with the highest accumulative. So we calculate the whole trajectory reward, and then select only one candidate for the rest of the generation. And then we get the final video. So this is just an algorithm of our method. So this is like we do T steps of the diffusion generation, and in the we have search scheduler S. So in this, if we want to search in some specific steps, then we do this resampling strategy and the final pruning to get the final candidate. This is how can we train this latent real model, because we try to evaluate pure noise actually, because in the latent is a pure noise. Because previous paper also mentioned that it's impossible to evaluate such a pure noise, but we show that it actually is possible to do this in a very earlier step. In this, our model is based on the Queen V language 2.5. We only fine-tune this latent petrifier and the VIT model. So the input will contain the latent features, the time step embedding, which is the denoising step, and also we have we get the latent tokens, we have the instructions, some metrics we want to evaluate for the video, and also the prompt, which is used for the video and the text alignment. And for training this model, we have two loss functions. The first one is just the regular regression loss, which is we have three metrics here, which is vision quality, motion quality, and text alignment. And also inspired by the reinforcement learning, we also use prevalence loss here, which will, for example, we'll have some pairs at we have the pseudo ground truth of tells us like which one is better than another one. Then we can add this prevalence loss to do the optimization as well. So in here's a summary of our strategy. So we are the first latent real model, and then we construct some data sets to train this latent real model, and also we propose a new resampling strategy. Here is just a quick video of our results. The left one are all from the baseline model, and the right one is from with our searching strategy. So this one's a bear with the atlas with a deer, and this one's butterfly changes the color. This one's mine is riding a bike. This one's two sheep, white sheep are eating grass. And also we compare with different other methods. This like the noise optimization methods and the searching methods. And our methods can improve the model, the generation quality, and also improve the efficiency of the generation. Yeah, this is just a very quick interest of our paper. Thank you. Yeah, we'll release our paper and the code very soon. Yeah, thank you.
So, any question?
Just a quick question: what video quality do you use for the reward? So,
the quality you mean for the reward model
Yes.
or the final? We use the motion quality, visual quality, motion quality, and text video alignment.
yeah,
the three
yes.
metrics.
So the first one, which model do you use? So
The whole model is used based on the Queen V language 2.5, but we also used another video reward model, which was pre-trained on the real videos. We use some pre-trained parameters from that model.
okay,
You can, the name of that paper is Improve the Video Evaluation Based on the Human Feedback. You can check that paper.
Yeah, got it.
All right.
Thank you.
Nice, thanks.
Thank you.